Next lecture, we will now study frequency and phase modulation. This will be the last lecture of communication system. So till now we have seen that we can vary the amplitude of a signal with respect to the message signal, and that will be the basically, if we denote your carrier signal by phi of t a cos omega c t, that is, I represent that by theta of t. Theta of t is also called angle of this cosine signal or phase. Okay, so what we have seen in amplitude modulation, suppose we have a cos of theta t, where theta of t was usually taken as 2 pi fc t, and we can have some phase lag also, theta naught. Although this doesn't matter, we can put it equal to 0 also, is a constant phase. Now we use it to vary A with message signal in amplitude modulation, whether it is DSBSC or AM. So this AU is equal to M of T in case of DSBSC, or A is proportional to M of T, message signal. That is for AM, right? Amplitude modulation. But we can have one more thing. We can, instead of varying A amplitude with the message signal, we can vary this theta of t with message signal. We can make it proportional to message signal, right? Or we can make frequency proportional to message signal. Okay, so this type of modulation where we vary this phase or angle with message signal is called angle modulation or frequency phase modulation. So now suppose if you take theta of t as 2 pi fct plus theta naught, then we know that if you differentiate, if you want to get frequency out of this theta of t, what will you do? You will differentiate theta, d theta of dt, and you will get 2 pi fc. 2 pi fc is the angular frequency, so derivative of angle of cosine or derivative of phase is equal to omega c. So this has a fixed frequency, so omega c is equal to 2 pi d theta upon dt, and it is also equal to 2 pi fc, right? So we can say that fc is equal to 1 over 2 pi d theta upon dt, right? See here, this time varies linearly. This theta of t varies linearly with time. In general, if theta of t has arbitrary dependence on time, a general angle, how to get something called instantaneous frequency? The frequency will change with time, but we can define instantaneous frequency in the same way as we define instantaneous velocity in physics. So that will be defined as omega I, instantaneous angular frequency, is equal to derivative of the angle with respect to time. And if you want to get Fi, that will be omega I by 2 pi, right? Yeah, 1 over 2 pi d theta upon dt. We can write that. So this omega I will be function of time, right? This in general, okay, because theta of t will vary, okay, may vary arbitrarily. We will see it soon when we will do the FM and PM, that when we make theta to be dependent on message signal, frequency will become function of time. Now theta of t can be written as equal to integral of omega it dt, right? Integration is reverse of differentiation, so very simple relationship. We have to use dummy variable alpha here inside, and minus infinity to t are the limits. Okay, so verification, we can again differentiate d theta upon dt, and using Newton-Leibniz formula of calculus, we will get that it is equal to omega I of t. Okay, so now if we make this theta of t to vary directly with a message signal, this is the case 1. If we make this theta of t to vary with message signal m of t, that is we can write theta of t equal to omega ct plus some constant times, okay, there will be some phase lag plus some constant times kp, I write m of t. Okay, so what we have done, we have made the theta, that is the phase or angle, to be proportional to message signal. So as message signal changes, this phase will now change. Okay, so this theta naught is arbitrary, we can take it equal to 0. So this type of modulation wherein phase changes with message signal is called phase modulation. Okay, we can put theta naught equal to 0, it doesn't matter. So theta of t is equal to omega ct plus kp m of t. Okay, this is the relationship for phase modulation. And our phase modulated signal we can write as, I denote that by phi pm of t, that is equal to a cos omega ct plus kp times m of t. Okay, so later on we will see some how to plot phase modulated signal for a particular message signal. Here the amplitude a remains constant, we don't vary a, rather the information about message is hidden in the phase. Okay, how the phase varies. So this is the case of phase modulation. But we can do another thing, we can make frequency to be proportional to this message signal, that's called frequency modulation. Okay, so what we do in frequency modulation, we make the instantaneous angular frequency omega I proportional to m of t. Okay, now we just saw a few minutes back that omega I of t is equal to omega c plus kf m of t, right? So we are making it, okay, so this is how we exactly vary the instantaneous frequency. Omega c is the constant carrier frequency plus kf m of t, we are making instantaneous frequency proportional to the message signal linearly. Now hence we can write phase frequency modulated signal as a cos theta of t. Now what is theta of t in terms of omega I of t? We just now saw that theta of t is equal to integral minus infinity to t omega I of alpha d alpha. Alpha is a dummy variable, okay, don't get confused with it. So we can write this as omega c plus kf m of t. So since we assume the causal process, so from minus infinity to 0, so the communication doesn't start, so we can write this integral as omega c omega ct plus kf times integral m of alpha d alpha. So we can take limit from 0 to infinity also here. Okay, so hence we can write this is your now this is the phase, and hence the fm signal can be written as a cos of omega ct plus kf integral 0 to infinity m of alpha d alpha. So far so good. So these are the two types of, this is the fm and earlier we had pm. Okay, so you need to realize it that how to differentiate between pm and fm, at least when we write the mathematical expressions of the two modulations. So in pm you will see that the phase term is directly proportional to the message signal, hence pm signal will be written as a cos of omega ct plus kp m of t. Kp is a proportionality constant, we will see its significance. Similarly phi f m of t is a cos omega ct plus kf now, but it will be integral of m of alpha d alpha, because we are varying the frequency, which is integral of the phase, derivative of the phase. Okay, so this is the mathematical formulation of phase modulation and frequency modulation. So But when you will modulate a signal using frequency modulation or phase modulation, they are inseparable. You cannot differentiate between the two. If you see the signal of FM or PM, you cannot see which one is FM, which one is PM. This becomes clear. See, suppose if you have phase modulator, if you design somehow phase modulator, from phase modulator you can design frequency modulator also. Look how, see what does phase modulator do. If you, if the input to phase modulator is message signal, right, then we will get this phase modulation. Now if the input is integral of message signal, how to get integral of message signal? We will use a circuit called integrator, and the input to integrator will be message, and we will get integral of message signal, and hence that will generate frequency modulation, right, because we are integrating the message. Now similarly, if frequency modulator, suppose you know frequency modulator and you design frequency modulator, how we can convert it into phase modulator? So for that, what should we do? Okay, so we will feed in here the derivative of the message signal, right? How to get derivative of message signal? We will use differentiator, another op-amp based circuit you might have studied. It takes m of t and output is d upon dt of m of t. Now the output of this frequency modulator will be the phase modulated signal. This shows that the FM and PM, they are in some sense inseparable, and we can use one modulator to get the other modulator. Let's see some examples. Suppose this is the message signal. Okay, it's triangular wave m of t. Let's say the value varies from -1 to 1, and the time interval is 2 into 10 to the power minus 4 seconds between the two peaks. Now let's see how phase modulated signal will look like. To look into that, so here is the mathematical expression: a cos of omega ct plus k p m of t. Now look at it. As m of t increases, this phase and hence the frequency will increase. Hence the fluctuations in cos will increase as m of t increases, and fluctuations in cos will decrease as m of t decreases. So hence we can draw the phase modulated signal as, initially m of t is having minus value, less value, so the initial frequency of this wave will be low, slightly low, right? So we can start, so here is it. So we can start drawing the initial part of this. So now m of t is increasing, it is going on increasing. As it increases, frequency will increase, then m of t is again decreasing back and frequency will decrease, then again increasing, so on and so forth. So initially, let's suppose I start drawing here. So here is the frequency. Now it will start, frequency will start increasing, see, because amplitude has increased of m of t, and it will reach to peak frequency here, then again it will start decreasing. Okay, and then again it will start decreasing and then increasing again, right? I am not able to draw amplitude properly. Amplitude remains the same. Now information is about message is hidden in the change in frequency. That is very, very important. It is hidden in change in frequency. Very high frequency means message signal has high amplitude, low means it has low amplitude. So similarly, FM, what is FM? A cos of omega ct plus kf integral m of alpha d alpha. Okay, now first you need to integrate the message signal. See, message signal is a triangular wave. Its integral will be, it will be parabolic type, right? So it looks like a sine wave, but it is actually, these are the parabolas. So again the same effect, this frequency is increasing, and as frequency is increasing, sorry, the message signal amplitude is increasing then decreasing. So accordingly frequency will be first less, then increase, then again decrease, then again increase, and again decrease. This increase and decrease in frequency contains the information about message signal. Okay, that's very important. And you can see that we cannot easily differentiate between PM and FM. If someone shows you these two signals, modulated one, you cannot see which one is PM, which one is FM easily, just by looking at the modulated signal. Okay, so in this way you can say that FM is immune to noise because frequency does not get changed with noise, whereas amplitude changes with noise. So this is one advantage of FM, that it is immune to noise. Okay, that is why it is used very widely. All the current FM stations on mobile, they use FM. Okay, now let's consider again this your carrier signal. Suppose you denote this x of t by a cos of theta. I can see this relationship. E to the power j theta is cos theta plus j sin theta divided by 2. So this relationship, why I have written here is, whatever information cos contains about a and theta, the same information e to the power j theta contains about, angle and amplitude, because cos theta I can write as real part of e to the power j theta. Why we use this notation? Because there are a lot of mathematical simplicities when we use e to the power j theta rather than cosine and sine. As an example, if you want to prove cos of a plus b is cos a cos b minus sine a sine b. So there is a trigonometric way which is hard, rather than if you instead of take e to the power j a plus b, which you can write e to the power j times e to the power b, and then expand e to the power j in terms of cos and sine. So cos a plus j sine a, cos b plus j sine b, right? And take real part on both the sides. So real part of e to the power j a plus b and real part of this. We know that real part of e to the power j plus b is cos of a plus b, and on right hand side you just see the terms without j and you will get a required relationship very easily. So we will use this concept to derive the bandwidth of FM, bandwidth of frequency modulated signal, or the same applies to phase modulation. So first of all, in frequency modulation, this term appears repeatedly, m of alpha d alpha integral. I will represent it by a of t so that I don't have to write this integral again and again. Okay. Now I will take the FM signal. So we know the FM signal can be represented as phi FM of t is equal to a cos of omega ct plus there is that kf integral of m of t, which is here a of t. A of t represents the integral of m of t. Now how can we represent the same in complex notation? The complex equivalent for, okay, so kf kp constants are f for frequency modulation, p for phase modulation. Okay, so these values are arbitrary constants. They are in our control. We can change them and it will have effect on bandwidth, as we will see soon. So the complex equivalent of FM, that is e to the power, this is the complex equivalent or complex representation of FM signal. So this will be equal to a e to the power j theta. Theta is here omega ct plus kf a of t. Now you see, if you take real part of this phi hat fm, you will get phi fm of t back. Okay, and you will soon realize why I have done this, because it will help in deriving the bandwidth easily as compared to if you take the cosine formulation of fm. Now I can write this phi hat fm as a e to the power j omega ct times e to the power j kfa of t, right? Now let me take this e to the power j kfa of t. I will use the power series or the Taylor series for exponential function 1 plus j kf at plus j square is minus, hence is minus kf square by 2 factorial a square t plus so on so forth, right? Higher order terms. And now up to this is the nth term and so on so forth, e to the power n a of t plus so on. Now I can write phi fm hat of t is equal to this series a times this Taylor series of exponential function minus kf square by 2 factorial a square t and all these terms, okay, times e to the power j omega ct. Now e to the power j omega ct can be written as cos of omega ct plus j sin omega ct. I will take real part of this. I know the real part of phi hat of fm is the phi fm signal, okay. So on the right hand side, if I combine the real part and write that, so how will I do that? First let me multiply this Taylor series with cos omega ct plus j sin omega ct. Now you multiply all the terms and you separate the real part and imaginary part. So what will you get? So first term will be a times cos of omega ct, then kf a of t sin of omega ct. Just verify it. It's very simple multiplication. So I have written all the real parts on one side and then plus j times bracket start all the imaginary part. So we don't care about imaginary part because we have to take real part of it, okay, whatever is the imaginary part. So real part f phi fm of t is equal to real part of phi fm hat of t, and hence that will be equal to this a cos omega ct minus kf a of t sin omega ct minus kf square by 2 factorial a square of t cos omega ct, then plus kf cube by 3 factorial a cube of t sine. So the sine and cos will appear interchangeably, and then so on and so forth. So this is another way to write the FM signal. This gives us more easy way to compute the bandwidth. Now see, the first term is cos of omega ct. See, a of t is m of alpha d alpha. Let's say that message signal has bandwidth. It is a band limited signal. Its Fourier transform is some m of omega. This m of omega is band limited to some b bandwidth, something like this. Suppose this is the Fourier transform of message signal, so its bandwidth is b. Here is a fact which you should right now remember, that if you integrate time signal, then the Fourier transform of integral, the bandwidth does not change, okay, it will remain still minus b to b. Integrating does not change the bandwidth. This is the fact we are using here. It has a simple proof also, but we will not do that right now. So hence similarly the other fact is, if you have a square of t, a square of t is equal to a of t times a of t, right? We know that the Fourier transform of product of two functions is convolution. Now a of t has Fourier transform, suppose a of omega. So a square of t will be having Fourier transform a of omega convolution with itself a of omega. Okay, when you will convolve it, it is a basic fact, when you convolve a function with itself, then it's the x-axis, it gets doubled up. So what I mean is that it extends to tb 2b to minus 2b. okay, it's the result of convolution. You can easily verify it with some examples. So hence a square, just a moment, yeah, so hence a square of t has bandwidth 2b. Similarly, a cube of t will be a of t convolution with a square of t. Now a square of t has bandwidth 2b, a of t has b, so convolution will have bandwidth 3b. Similarly, a4 of t has bandwidth 4b, a n of t has bandwidth nb. There are such infinite terms in FM signal. When you add up all the bandwidth of all the terms, see there are infinite terms. It has bandwidth B, this term has bandwidth 2B, this term has bandwidth 3B, so on and so forth. When you add them up, there are infinite terms, which deduces that the bandwidth of FM frequency modulation is infinity. So bandwidth of FM is infinity. So the ideal, theoretical or mathematical and the exact bandwidth of FM is actually infinity. Okay, but then the question arises that why will we use it? Because we can't have infinite bandwidth. The answer is that not every frequency term is significant. So if you see the expansion of FM, so not every term is significant. In particular, we can design FM modulator in such a way that this kf we can put very small. So when kf becomes small, so we can neglect kf square, kf cube, kf4 higher order terms. So in such cases, we will not get infinite terms, rather we will just get two terms. So that type of FM is called narrowband FM. So this is what we will do, narrowband FM. Okay, so in narrowband FM, what we assume is that this constant kf or is very small, and message signal anyways or a of t that always has less value. So but we are assuming this kf is very small, so that we can easily assume that mod of kf times a of t is much lesser than 1, and it is up to designer. Okay, we can always design FM modulators in such a way. Suppose if kf is 10 to the power minus 2 or 10 to the power minus 3, then kf square is 10 to the power minus 4, negligible, right? So we can easily neglect higher order terms with such small values of kf. That is, such a FM is called narrowband FM. So what will remain there? Only first two terms will remain there. So hence narrowband FM will be written as the approximation of FM. A first term is cos of omega ct minus kf a of t sine of omega ct, the linear term of kf. All other quadratic and higher order terms of which contains kf square, kf cube will be neglected. They are very negligible. Okay. So now this resembles something you might have seen already. It looks like DSBSC signal, right? Or it looks like AM signal. So this equation gives us direct way to generate this FM. Here is one more fact. Suppose if we take two message signals with corresponding integrals a1 and a2, if you add them up and if you then modulate them as with FM, so you will get a cos omega ct a1 of t plus a2 of t, right? So for general FM, you will not get this to be equal to phi fm1 of t or phi fm2 of t, right? But in case of narrowband FM, since it is outside the sign, so you will easily get a1 t plus a2 t. You will get 5 fm1 of t, 5 fm2 of t. This is called that the modulation is linear. DSBSC is linear modulation. AM is linear modulation. General FM is not linear, it's non-linear modulation. Superposition principle is not satisfied. Similarly, PM narrowband PM can be represented as a cos omega ct minus kp m of t sine omega ct. Okay, so instead of what is difference between PM and FM? In PM there will be kp m of t. In FM it will be kf a of t. A of t is integral of message. That's the difference between FM and PM mathematically. So if you look like, it looks like AM signal. That is what I was saying. A cos omega ct plus m of t cos omega ct. Now these two mathematical equations give us very easy way to design or develop their modulators. Modulator for FM and modulator for PM. And you see what is the bandwidth of narrowband FM? It is same as the bandwidth of DSBSC signal, right? You know that if m of t has bandwidth b, m of t sine omega ct or m of t times cos omega ct has bandwidth 2b, right? That is the basic fact. So hence narrowband FM has bandwidth 2B. So now we will see narrowband FM modulator. So what should we do? We have to do these two things in the modulator. One is we have to get A of t multiplied with sine omega ct. That is one job. And then we have to add cos omega ct to the that signal, right? So here is first of all equation narrowband FM A cos omega ct minus kf A of t sine omega ct dt. I think A is common. Yeah, A is common. Right. So I will put a bracket here. Now, how to get A of t sine omega ct? You need to multiply. So any DSBSC modulator will do this job. So if you have a DSBSC modulator, you feed in A of t and carrier signal as sine omega ct. The output will be some constant times A of t sine omega ct. That constant we can fix that as kf. You see, this is DSBSC modulator, any DSBSC modulator, ring modulator, bridge modulator, whatever you use. Here is A of t and here is minus A sine omega ct. Okay, we put the minus sign here, and the output of this will be minus A kf A of t sine omega ct. This can be done. Now what is the other part which we need to do? We need to generate cos omega ct and add it up. How to get A of t? Of course I have to use integrator, and to the integrator I will feed in the message signal m of t. Okay, now how to generate sine omega ct? I will actually generate cos omega ct, and here I will use the oscillator which will generate A cos omega ct. Then I will use pi by 2 phase shift. Cos theta plus pi by 2 is minus sine theta, so that will give me minus A sine omega ct. Okay, now this cos A cos omega ct, I will use adder after this. So here is A cos omega ct. Now I will use the adder here and I will add it up. So the output is exactly phi FM narrowband. Okay, narrowband FM. Very simple modulator. You haven't used anything new. You already have all these ingredients. You can easily design it in lab. Now similarly, phase modulator. For that you have A cos of omega ct minus kp m of t. So instead of A of t, there is m of t. So we don't need integrator here. That is one difference. So m of t, then directly DSBSC modulator, and to DSBSC modulator the other thing that comes as input is minus A sine. How to get minus A sine? I will use cos and then pi by 2 phase shift A cos omega ct. Okay, minus A sine omega ct. Okay, then I will add these two up and I will get phase modulation, narrowband phase modulator. Very simple modulator and demodulator design for frequency modulation. So this much for this lecture. So lot of things are left, but for examination purpose this much will be there. Okay, so I hope you understand it. So if you have any doubts you can ask me. So watch this video and again and again, and try to practice it